you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T, and today I have a tutorial on functions and inverse functions. Now, we've used functions most of the year, and so some of which we'll be talking about in this tutorial will be review of that, but we'll be extending functions to more elaborate operations of functions and also introducing the concept of inverse functions. So if we remember earlier in the year, we can think of a function here, the function called f, as a machine. Machines take inputs, they massage the inputs and produce an output. So we could think of a soda machine in the cafeteria where our input is money, but also a code that you punch in. And depending on the code, and you put in the right amount of money, out pops a soda, the particular one that you asked for. So there's a one-to-one mapping. So for each input, there is a defined output. Now, the reverse is not necessarily true. For each output, there may be more than one input. So on the machine, for some of the popular flavors, there might be multiple codes that give the same output. In math, the function, the operation, the gears inside the machine are defined as a algebraic operation or expression. And the input can be numbers. They can also be expressions. Function notation has two parts. Function notation has a function definition. So again, this is not f times x. This is the function f, which has an input of x or whatever variable we're using here. And it won't always be f. The function names are in algebra are one letter. It could be whatever appropriate letter. And it equals some rule, some formula that will calculate the function value. So this is the function definition. And then when we use the function, we are asked to evaluate or find a value of a function. To do that, we will be plugging this value into the function. So this is a compact way of stating in English this. So this down here means for the function defined as y equals 3x squared plus 2x minus 1, evaluate for y given that x equals negative 2. So again, mathematicians like to be compact. So here's some sample problems doing function evaluation, and then we'll talk about function operations. So again, to evaluate a function, we are going to substitute the given value for all the letters t in the equation. Now the only issue that we need to be careful about, especially when you're using a calculator, is to pay attention to these signs. And some of you've had issues all year long when you've squared a negative number. You enter it into the calculator like this, and the calculator gives you negative 36. Because the calculator does not know that this negative is part of this number. It treats it as the negate operation or a subtraction, and it does the exponent first. We want to, in this case, square the negative 6, so we need to make sure we put that in parentheses. So when you're using a calculator with these negative numbers on the functions, make sure you're careful. So here we're going to have 3 times 36, and minus times minus would be plus. 3 times 36, 18,108, plus 36 gives us 144. So that's our value of h of negative 6. Now again, the answer is this number. We're not going to solve, we're not solving for a letter here, so we're not going to divide by negative 6. This is not h times negative 6. We can evaluate functions using expressions. So the same step. The first thing we do is substitute our expression for each of the x's. And now we simplify. So here we have x plus 1 times x plus 1. So we can use FOIL to expand that. And here we can distribute the -2. When we FOIL this in combine like terms, we're going to get that expression. And now we can combine like terms. So this -2 and that -2 cancel each other out, and so we end up with x squared minus 1. Again, that's the value of this function operation. Now functions, just like numbers, can be added, subtracted, multiplied, divided. So this will be one of the notations for subtracting the g function from the h function. It could also be written as g of x minus h of x. So both of those mean the same thing. So we're going to take the g function and we're going to subtract the h function. Now notice what I've done here is I've put the h function in parentheses because we are subtracting the entire function, and it's important that I distribute that minus. For me, it's automatic that when I see a minus in front of a parentheses that I'm going to distribute. So by putting this parentheses around this, I won't forget to distribute the minus to that -3. So now if I get rid of the parentheses by distributing this minus, and now we can combine like terms here, and our final answer would be this. So that's this subtraction. Here again, g times f means we're going to take the function g of x and we're going to multiply it times the function f of x. And to multiply two expressions, we're just going to FOIL it. So 3x times x squared would be 3x cubed. 3x times -5. 1 times x squared. And 1 times -5. And now we just range it in standard form with the x's in decreasing powers. And we have our answer for multiplying two functions. Now, a more elaborate type of function operation is referred to as composite functions. So let's look down here at the picture. So in composite functions, we are taking an input and putting it into a function, and the output of that function becomes the input to the next function. Now we could think of this as making mashed potatoes. To make mashed potatoes, we have two main operations or functions. The first is we have to boil the potatoes. So if the f function is the boiling potato function, we put raw potatoes, x, into the pot and boil them, and after some period of time, out comes cooked potatoes. And those go into a second process, the mashing process, where you put the cooked potatoes into a bowl along with butter and milk or cream or something, mash them up, and out comes mashed potatoes. So frequently we take simpler functions and link them together as a composite to make more elaborate functions in mathematical situations. The notation can be either of these two notations, and this notation as well as this is read as g of, the parentheses that we use of in function notation, so g of f of x. And here, kind of this O you can think of as of, so g of f of x. So you'll see both of these notations. So let's look at some operations with that. So here we're going to do h of g of x. So remember that means, I like this other notation, it's easier to see. And when we operate functions, it's like mixing cups or measuring cups. They're nested inside. We always start at the inside. So we're going to replace g of x with its value, which was defined here. And then we're going to use the same thing we did earlier on function notation. We're going to put this expression into the h function. So we've got -2x plus 2 squared minus 4 times -2x plus 2. We'll square this, so we're going to get 4x squared. That's going to be minus 4x minus 8x plus 4, and distribute this minus 4. Those cancel, and we end up with 4x squared minus 4. Now, I'm not going to show that here, but if we had done g of h of x, we would likely get a different answer. So the order that we are doing the composites matters. Just like if we go back to the mashed potatoes thing, if we try to put the raw potatoes into the bowl and mash them before we cook the potatoes, that's not going to work. So we will get an answer when we do this composite, but it's likely to be a different answer. Let's try another one. So in this one, we have this original notation. Now remember, this also means g of h of x. So we're going to replace h of n with its value. And we're going to now plug that into the, whoops, I didn't want that. We're going to plug that into the g function. So this goes in here, so -2, and we're going to replace n with h of n. Now we can just use our algebra skills to simplify the expression, and that's as far as we can go. Now we can do composite functions with numbers. So we first need to evaluate g of 10. So it's going to be 3 times 10 minus 1, which is 29. And now that input is going to go into the h function. So that here we get 36, 816 negative, minus 2, which is negative 118. So you just work your way from the inside out. So evaluate the inside function. Sometimes it's just replacing it with its definition, and other times we are calculating by plugging in a specific input into the function. Now, one of the uses of composite functions is going to be for inverse functions. Inverse in math means something that undoes something else. So when we're talking about functions, an inverse function will undo what the original function did. If we look at that in the picture, we put a input into a function and get its output called f of x. Now if we use composite functions and take that output and put it into what's referred to here as the inverse function, we get back our original input. We undo what f did. So undoing it means giving you back x. So our terminology, if this is f of x, we use this -1 kind of exponent thing for indicating the inverse function. This is not an exponent. It would be read as f inverse of x. Now you can see this is the same diagram, except I looped it around, that we use when I introduce composite functions. So this will be the prime test, or one of the ways of determining if two functions are composites. I can process x through a function, then take the output, and I should get back x. So if I write it in composite notation, if I do it this way, f inverse of f of x, that's what this picture shows, gives me x. And for two functions to be inverse, not only do we have to be able to process the input that way, but if we do f of f inverse, so if we put f of x into f inverse first, it also has to give us back. So composite functions, undoing each other means you get back what you started with. So that's summarized here. So two functions are inverses. This stands for if and only if the composites give you x. So let's look at that for these problems. So let's look at here, let's do f of g of x, and we have to look at g of f of x. So we're going to plug g of x into f of x. So I've got 1/3, and now I'm going to plug 3x to the 1/2, that's g of x, and I'm plugging it in where this x is. If we use our exponent properties, we would be multiplying exponents here, so we have 1/3 times 3x, which gives us x. So based on that, f and g appear to be inverses. Let's check the composite the other direction. So now we're going to put f of x into the g of x. I'll simplify inside by multiplying by the 3. So we've got x squared to the 1/2, which gives us x when we multiply our exponent, x to the first. So the answer here is yes, those are inverse functions of each other. Let's look at number 2. So let's try f of g of x. So I've got 2 and then times 1/2 x plus 1 minus 1, which gives me 2 times 1/2 would be x, plus 2 minus 1 gives me x plus 1. So these are not inverses because we did not get just plain x. It might look like here I'm undoing a multiplying by 2 by dividing by 2, and I'm undoing a subtraction by adding, but they're not being done in the correct order. Also, these might look like inverses. To undo a cubed, we use a cube root. To undo this subtract 1, we add 1, etc. So let's see whether these indeed are inverses. So let's look at, let's say, f of g of x. So I've got here cube root of x plus 1 plus 2, and that's cubed, minus 1. Now, since I can't combine those and simplify those, if I cube these, I'm not going to just get x plus 1 plus 2 cubed. I would have to multiply this out 3 times. This is not going to be x. I can already see that that's not going to simplify to be x. So we're going to just stop at that point and say that these are not inverses. Now sometimes we'll be looking at inverse functions graphically, and so I've written 2 functions. In red is a linear function f of x, and in blue is the inverse of that function. And if we look at the graphs, I've also graphed this line y equals x. That's the 45-degree diagonal line where in every point here the 2 xy's match. So this is the point 15, 15, 10, 10, 5, 5, 0, 0. And if we look at respective points, these 2 graphs are symmetrical to y equals x. So inverse functions are always symmetrical across this y equals x line. And when 2 functions are symmetrical, if we take matching points and swap the x and the y, so this is x and y, and so this x becomes the y, and this y becomes the x, and get those points, we get the 2 functions. So we're going to use that property of the points being swapped in a second to come up with a procedure for finding the inverse of a function. But first, let's look at an example with a graph. So let's sketch and find the inverse of f of x. All right, so we're given this line, and we are being asked to graph its inverse. So as a guide here, I'm going to put a line for y equals x. And when we go to draw our inverse function, it needs to be symmetrical with that line. Now, since f of x is a linear function, I need to graph 2 points and draw a line through it. Remember from Algebra 1 and earlier this year, this number without the x is our y-intercept, our b, and this number is our slope. It's not stope, that should be slope. So we have a y-intercept at this point here, which is 0, 2. And now if I go up 2 and over 5, 1, 2, 3, 4, 5, we have a point here. and I'm going to connect those with a line. And I wanted that to be solid, so let's make that line blue, and let's also make it be a solid line. So a solid line, let's make the color blue. We'll extend this end here. So that's now f of x. This point was 5, 4. So now if we want to, from what we learned before, if we want to do f inverse of x, it's going to be a linear function, and we're going to have 2 points. We're going to swap the x and the y's. So let's plot those points, 2, 0, and the point 4, 5. And now let's draw a line through those 2 points. And let's fix the properties on that so that we can make that line red and extend it. Let's extend that line. And that's our graph for f inverse of x. If this was a parabola, then we would want to pick a few more points to get a nice curve, or if it was exponential, we might want to pick a few more points. But the process of picking points and swapping the x and y will always work. Now, since this is linear, we could actually write the formula for f inverse of x. It wasn't asked for. This is our y-intercept, and our slope would be up 5 over 2. So f inverse of x is 5/2 x minus 5. So let's wrap up this video. So when we were graphing, and we're going to do this without doing a graph, is we're going to write the function in y notation. And to swap the points, we're going to do that in function notation. So we're going to make the y become an x, and the x will become a y, and then we'll solve the equation for y, and then we'll put it back into function notation. So that'll become clear when we go through my examples here. So I'm going to write this as y equals -2 plus, I'm going to write this as an x. Now I'm going to change colors because we're going to swap the y for x and the x for y. So this blue function here, this is f inverse. But we want to solve it for y, so I need to add 2 to both sides. And we undo a cube by either raising to the 1/3 power or cube rooting both sides. So now I have the cube root of x plus 2. And on this side, if I cube root this, I just get y minus 1. And now to finish, I'm going to add 1 to the other side. So I'm going to get cube root of x plus 2. And then outside of the cube root, I have the minus 1. And now to finish, we want to put it back into function notation. So this will be called f inverse, and let's put it back to the letter we had in. So f inverse of n is going to be the cube root of n plus 2 minus 1. If we computed f of f inverse of n, assuming we did all of our algebra correct, we should get n. I'm not going to go through that proof because I'm sure I did all my algebra steps correct. And let's do one final one here. So we're going to make this be y. And now we're going to swap. I'm going to change colors here. You don't have to change colors, but we just need to know once we change the color, this is f of x, and this is now f inverse of x. So to solve this equation for y, I'm going to multiply both sides by 9. I'm going to now add 16 to both sides. So I've got 9x plus 16 equals negative 4y. And then we're going to divide by negative 4. So I have the equation either in this format, or I could simplify it by dividing by the negative 4 and put it in the normal format for a linear equation. Since this was in that format, we could leave here. So this is f inverse of x. This is also f inverse of x. So again, the whole key is just swapping the x and the y. So I hope you have good luck in working with this mathematical language of function notation and working with inverses.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you